We're exploring some different territory in this section as we look to uncover some characteristics of a new class of functions that we haven't yet tackled this semester. So I want to begin by first of all describing what an equation always looks like if it is an exponential equation or an exponential function. And that would be to have the dependent variable of y set equal to some number a raised to the independent variable x power. So basically you have x in the exponent when you have an exponential function, and then the base of that power is a number. So like if you have y equals 2 to the x, that would be an exponential function. Now it actually turns out that you do need that base of the power to be a positive number. And also, it would be kind of ridiculous to make the base be 1 because 1 to the x, no matter what x is like basically always going to be 1, right? So then it wouldn't really be anything fancy, right? Because it would just be a constant function. The fact that we need a to be positive is a really important thing because what happens if a is negative is then when you create a table of values to plot all of your points, you get like a not continuous graph, and like you can't even really actually really visualize it because you just get values that pop all over the place. And so that's why we restrict a to be positive, because we get very nice continuous nice graphs that are either exponentially growing or exponentially decaying, which we're going to talk about in a little bit. Okay. So we're asked here to graph the exponential function f of x equals 2 to the x. So we just do this by plugging in some numbers, right? Like you could just make a little table, and you can do most of this in your head. It should be pretty easy enough. So like if you plugged in, like 3 for x, let's say, well, that would mean that you would need to do 2 to the 3, which is 2 times 2 times 2, which is 8. So when x is 3, you should have 8, right? When you plug in 2, 2 squared is 4. When you plug in 1, then 2 to the first is 2. When you plug in 0, 2 to the 0, anytime you raise it to the 0, it's going to be 1, right? And then we should keep working backwards and be able to plug in like negatives or even fractions and decimals and whatever. So if you plugged in -1, that'd be 2 to the -1. But 2 to the -1 is the same thing as 1 over 2 to the first, which is 1/2. And then if you plug in -2, 2 to the -2 is the same thing as 1 over 2 squared, which is 1/4. And then 2 to the -3 ends up being 1/8, because that's going to be 1 over 2 to the third. Okay. So if we were to plot all of these different ordered pairs and plot -3, 1/8, and -2, 1/4, -1, 1/2, 0, 1, 1, 2, 2, 4, 3, 8, you get a graph that starts to grow really, really fast as you move to the right, and then over here at the left, it gets really, really, really close to the x-axis, but it doesn't actually approach. So we actually do get a horizontal asymptote there of y equals 0, because that's the equation for the x-axis. Okay, and that's what our graph looks like for y equals 2 to the x. So what we have happening right here is actually a graph that we could classify as exemplifying exponential growth, because as you move from left to the right in the graph, the y values are increasing over time, right? And actually the graph is strictly increasing, so it's always going uphill. It never flattens out ever, and it's never decreasing, so it's a strictly increasing graph, okay? Now when we examine this graph, we basically just have the reciprocal of 2 as our base this time, so 1/2. We're going to see a really strong connection between the graph of this graph of g here to the graph that we just graphed with y equals 2 to the x. So if we just make a little table of values right here and plug in some numbers, how about plug in 0 first, which would mean we do half and raise it to the 0 power by plugging 0 in for x. That would make it equal to 1. And then if we plugged in 1, half to the first power would just be half. We plug in 2 and we do half squared. That means we would do half times half, which is equal to 1/4. And then if we plug in 3, half to the third would be equal to 1/8, because it's half times half times half, right? Now, if we work backwards and we do like a -1 exponent, that's really just going to reciprocate the base. So since our base is currently 1 over 2, it's going to flip it and become 2 over 1. So yeah, 2 over 1 is indeed 1/2 to the -1 power, which is then just 2. If we had a -2 exponent, then 1/2 to the -2 would be the same thing as taking 2 over 1 and raising it to the +2, which would be 2 squared, so that's going to be 4. And then you can guess, okay, -3, well, it's going to be 8, right? So, of course, you can see that really strong connection between when it's raised to a -3 power versus a 3 power, or -2 versus 2 power, and -1 versus 1 power, because how 8 and 1/8 are related, and how 4 and 1/4 are related, and 2 and 1/2 are related, are just reciprocals, right? Okay, so you can plot all of these values. So the ordered pair -3, 8 would be right here, and -2, 4, -1, 2, 0, 1, 1, 1/2, 2, 1/4, 3, 1/8, etc. And it's going to keep going by these powers of half, right? Just like this. So basically, your graph is just kind of flipped sideways from the graph that we had just graphed right here. Okay, so what we have in this type of a function is when it's like decreasing like that exponentially, it's exponential decay instead of exponential growth because of the decrease in y values as we move from left to right, right? Um, yeah, beautiful. So you'll notice that actually you can very easily figure out whether it's going to be growth or decay based on whether your base is a certain type of number. So these graphs right here were all exponential growth. And that's because the bases are like 4, 2.5, and 1.8. So the bases are actually greater than 1 in those cases. Versus here, where you have exponential decay happening, these bases have to be numbers that are less than 1, so that then whenever you multiply a number that's less than 1 with itself, it just becomes smaller and smaller and smaller the more you multiply it with itself, right? But because the base of an exponential also has to be above 0, these are bases that are just strictly between 0 and 1 then, okay? So that's how you can tell the difference between when you've got exponential growth, like you've got there, and then exponential decay, right? I'm going to take a little bit of time right here to be able to talk about reflections in graphs of functions because it's something that we're going to have to do in terms of transformations of exponential functions in a little while. So let's suppose that this function that you have right here is the graph of y equals f of x, right? And we want to graph some different sorts of reflections of these. So what we could do to be able to create this reflection right here, which would reflect in the x-axis, is to have the same x coordinates, but the y values are going to be opposites of one another. So basically, this should be y equals negative of f of x to be able to have opposite y values. And so then it turns out that actually, whenever you have negative of f of x, that is going to be a reflection of f of x in the x-axis. So when I say that it's in the x-axis, that means that it flips over the x-axis, okay? If you wanted to take this graph right here and flip it sideways, then it's going to look, something like that. And what would happen is you would have opposite x coordinates but same y values. So this graph right here ends up being the graph of y equals f of negative x. So you have opposite x values, but the y values are still going to be the same. And so, yeah, whenever you graph f of negative x, it is always going to be a reflection of the original graph of f of x. And it reflects in the y-axis because it's going to reflect over that particular line, right? So if you take this graph and you reflect it sideways, and then if you take this graph and you reflect it upside down, it would create a graph that would look something like that. But it would also be like the same thing as if you flipped it upside down and then sideways, right? So it kind of does both of those things of reflecting in the x and reflecting in the y, which then means that if you have negative of f of negative x, then that is going to be both a reflection in the x-axis as well as in the y-axis, okay? Well, you're going to see how this plays out when we look at equations that have negative x instead of positive x in it, or if we negate the function, and how that plays out with reflections. Okay. So before we get there, just a little bit of other foundational information before we start meshing it all together right here. So we need to be able to establish a really good, strong understanding of what just graphs of exponentials are going to look like. So you see at the far left right there, we've got 1, 2, 3, 4, 5, 6, 7, 8 different equations. The first four all have a base of 3. And the second 4, 5, 6, 7, 8 there all have bases of 1/3. We want to match them to the graphs, okay? So what you should be able to recognize with the first four is because the base is equal to 3, which is greater than 1, you should have a graph that would be exponential growth if you had just y equals 3 to the x. And so the one that really is exponential growth out of the graphs that are shown right here is the graph of b right here. And so that actually is what the graph of number 1 is graph b, okay? So what you see happening in number 2 right there is this is 3, but now with a negative x. So when you plug in a negative x, this is now like f of negative x, if originally f of x was just 3 to the positive x. So when you plug in a negative x, it flips the graph sideways, so in the y-axis. So since we knew that this graph right here was 3 to the positive x, then if you just flip that sideways, that should be 3 to the negative x, which would be what D looks like, because that's the sideways version of it. So this right here is going to be graph D. In this equation, in number 3, you have a negative in front of 3 to the x. So that means that we're actually just really making f of x become negative. So this would be f of x, but now negative, which always flips the graph upside down or in the x-axis. So we would again go back to our original parent function of 3 to the x and flip it upside down. And the upside down version of that would look like this in graph A. So this is going to be graph A. And then the last little guy that you have right here is negative 3 to the negative x. And for that, it would reflect in both the x and the y, right? And so it would end up looking like C, because if you reflected it sideways, it would become looking sideways would look like D, and then if you reflect that upside down, it would turn into C, right? Okay. So then we need to be able to examine what's happening in 5, 6, 7, and 8 as well. Okay. So these ones all have a base of 1/3. So 1/3 is a number that is less than 1, which means that the graph should be exponential decay if we're looking at just plain 1/3 to the positive x. And so that graph is going to be above the y-axis, but it should be decreasing over time, which is really what graph D looks like right there. So that is going to be what this number 5 graph looks like, is graph D. Okay. So then when it's negative x, it should flip it sideways. So the sideways version of D is graph B actually, right? And then this one has the negative in front, so it should flip graph D upside down. Look at the one that's upside down, it's C. And then finally, graph D, when it gets flipped sideways and then also upside down, turns into graph A. Okay? All right, so also applying that in some other sort of contexts, here we're asked to describe the transformations of the graph of the function from f of x equals 2 to the x. So in general, whenever you have a function that is of this form, f of x minus h plus k and multiplied by a equals y, we know that h always shifts the graph left or right, and k is going to shift the graph up or down, right? And then this factor of a that multiplies in front will either do a stretch or do a compression to the graph, depending on whether that number is bigger than 1 or less than 1 and whatever, right? Okay, so for this function right here, we're asked to describe the transformations compared to just y equals 2 to the x. So this right here, 2 to the x plus 3 minus 5, is really like y equals f of, but then we plugged in x plus 3 instead of x, and then we're subtracting 5. And so because that plus 3 is plugged in with the x, it should be shifting the graph to the left 3 units. And then subtracting 5 is going to shift the graph down 5 units. So those are the only transformations that we're going to have in comparison to just 2 to the x, right? So this would be y equals 2 to the x, but then left 3 and down 5. And that would be the graph of g, right? Cool, cool, cool. Okay, this one has a couple things going on. So the fact that it's being multiplied by a negative means it's going to graph the graph upside down. So we would describe that more succinctly as a reflection in the x-axis, because that's the line it's going to flip over is the x-axis. And then the subtraction of 1 right there where the x is plugged in is going to shift the graph to the right 1 unit. Okay, and that's all that's happening there. With this fella, I guess there's probably three things happening with this. So for one, you're multiplying by a 3 in front. That is going to vertically, and because 3 is bigger than 1, it's going to vertically stretch the graph by a factor of 3. So it's just going to make it grow faster vertically, right? And then now that we've plugged in a negative in front of the x right there, that does flip the graph, but it reflects it sideways. So we're going to have a reflection in the y-axis when it reflects sideways. And then plus 2 means that the graph gets shifted up by 2 units, okay? And then finally, this last little example right here has several different things going on. Actually, lots of stuff going on here. So you could write this in a little different order if you wanted to. You could write it this way, and then it might make more sense to you in terms of what number corresponds to what transformations. So the fact that you have a negative coefficient in front of the 2 to the x thing means that it's going to reflect the graph upside down. So you do have a reflection in the x-axis because of that. Okay. And then let's talk about this right here next. So plus 1 just means it's going to shift the graph up 1 unit, of course. Okay. What's happening here is a little bit funky because you actually need to think about that as being negative of the quantity of x. And then if you factored a negative from the positive 4, then it would actually be minus 4. So then you need to consider the fact that that negative means you're going to reflect the graph sideways. So it reflects in the y-axis. And then you actually need to use this right here that it's subtracting for to determine if it's gone left or right. So you don't look at it directly from the plus 4 right there. So when you look at the minus 4, that means that it shifts to the right 4 units then. Okay, so whenever you have that negative as a coefficient of x, you've got to factor out that negative and then look at what's in the parentheses after you factor out the negative to determine if it's gone right or left accordingly. Beautiful. So let's graph some functions, right? So this graph is really just going to shift to the left 3 and then down 5. So I think just the easiest way to go about this is schedule out what 2 to the x looks like, which would just be, 2 to the first is 2, and 2 squared is 4, and 2 to the third is 8. 2 to the 0 is 1, and then we know it's half and 1/4 and whatnot, right? So you get your graph like that, and then all you need to do then is just be able to go to the left 3 and then be able to go down 5. So if you just take that graph and you go left 3 and then down 5, okay, then voila, there you're at. Right. So it'll obviously take you a little bit more time if you're doing this paper and pencil, but so just like sketch 2 to the x first, and then sketch a new graph on the same graph of that, and it'll be done, right? Okay, then if we look at this little fella right here, what I would highly recommend doing is before you do any left-right movement or up-down movement, so any of the translations, is to take care of any reflecting and stretching, and then you can just shift it up or down and whatever. So what I want to start with right here is I want to start with graphing what y equals negative 2 to the x is, and then because of the minus 1, then we'll shift it right 1 unit afterwards. So this graph right here should be upside down of 2 to the x. So it would be the upside down of what that looked like, because that was 2 to the x. So it should actually go to a negative 2 when x is 1, and a negative 4 when x is 2, and a negative 8 when x is 3, and all these other points, right? Okay, so this would be what y equals negative 2 to the x looks like. And then all we need to do is to then just shift it. So once you've sketched that out on your graph, then you can sketch a new graph or whatever, or you can just figure it all in your head at once. And let's see, did I move it correctly? There we go. That would be right 1, and it should look something like that. Okay. And then for this fellow right here, I would definitely take care of the translations last. So we do need to go up to, but we'll save that for later. It does need to reflect in the y-axis, so go sideways. So we'll try to take care of that almost right away. And then we also do need to stretch the graph by 3. So maybe what I'll do is actually I'll do this part here first, is the stretching. And then we'll do the reflecting second, and then we'll save all the up-down movement for last. So what I'm going to start off by doing here is I'm going to graph just y equals 2 to the x to begin with, which will look something like this. Okay. Now, the fact that it's stretched by 3 means that you want to triple all the y values. So when it has a y value of 2 right there, it should now actually have a y value of 6. And right here, where it currently has a y value of 4, you triple that, it should have a y value of 12. And right here has a y value of 1, so 3. Right here it's 1/2, so 1.5, etc. Right? Okay, so I'm going to erase that right there, and so it's going to look something like this. Okay? So it grows a lot faster because it gets higher sooner, right? Good, good, good. Okay, now that graph does need to get reflected sideways because of then the reflection in the y-axis. So then just kind of create the mirror image of all of those points. So something like that. So then we'll have to go with this new orange graph, of course, right? So voila. And then that graph now just needs to be shifted up 2 units. So I'll just take that and drag it up a couple units. The y-intercept will be at 5 now, and so something roughly like that would be the graph of that function. And then finally for this last little fella, okay, so just as a reminder here, we treated this earlier as negative of 2 to the negative of x minus 4 plus 1 equals y. So let's take care of these reflections that are happening. So we do need to reflect in the x-axis upside down, and then we do need to reflect in the y-axis sideways. So when that is all said and done, then when this reflects upside down, then it becomes like this, and then when that reflects sideways, it becomes like this. So it should look something roughly like that, which then means it should be going through -1, -2, and -2, -4, and -3, -8, 0, -1, that point, etc. Right? So that takes care of all the reflections. And then we don't have any stretching or anything, so just translating. So it's supposed to go right 4 because of the -4 in the parentheses right there. And then also up 1. So if we go to the right 4, and then we go up 1, it'll be like that. And we're golden, right? Lovely. Okay, we're also finding the domain and range of each of our exponential functions right here. So it's something that we could have done as we were graphing our different functions, but it's something that I really want you to kind of just off of a sketch be able to kind of figure out. So if we think about this first function right here and trying to figure out the domain in the range, try to think about what the graph would look like. So specifically if the base right there is greater than 1, you know that this is going to be exponential growth, so it should have this sort of shape as it gets higher going from left to right. And then the graph also gets shifted up by 4 units. So as just kind of a rough sketch of the graph, then what should be happening then is it should have a y-intercept at 0, 5, and then be asymptotically approaching this y equals 4 line right there, but never actually hit it, and then go towards infinity, okay? So the domain of an exponential function is actually all real numbers. And that's because you can plug any sort of numbers you want into an exponent. It can be a negative exponent, it could be a fraction exponent, decimal, positive, whatever, zero's fine, okay? But then for the range, it stays entirely above that y equals 4 line. So the range would be 4 to infinity with a parenthesis on the 4 because 4 is not a member of the range. It's not an achieved y value at all. Okay? So for this guy right here, this is -5 to the x. So it'd just be like an exponential growth because of the base being greater than 1, but then it's going to be flipped upside down. So if you take an exponential growth, but you flip it upside down, then it looks like this. Okay. So your domain then should be all real numbers, but then your range would be only numbers below the x-axis, which would start from negative infinity then and go up until you get to 0, but not include 0 because it never hits the x-axis. So parentheses on both ends of the interval there. And then just a last little example right here. Because of the base of 1/3, you do have an exponential decay to begin with, and then we'll start applying some transformations. So we do need to flip the graph upside down. So then that's going to change it to look like that. But then, so this right here, you'll want to think about that as being negative of x minus 1. So then that negative means it's going to reflect sideways. So then it should look like that when you reflect it sideways. And then we do need to shift it to the right one and then also go down 4. So it'll look something like this. So the fact that it's gone down 4 means that you do have a horizontal asymptote right here at y equals negative 4. That'll help you find the range. So the domain is going to be all real numbers still. It's true for any exponential function. And then the range would be only numbers below negative 4. So negative infinity all the way until you get to negative 4. Okay? So they should be kind of easy enough things that you have a rough picture in your mind, or you just kind of sketch it out. You can pretty easily figure out what the possible inputs and possible output values can be in exponential functions. Okay? All right, I want to look at a specific application. So skipping ahead to this one right here involving exponential functions. So in this application here, we have the exponential function h of t, which equals 80,040.68 times that base of 1.0481 to the t, where t is the number of years after 2015. And this can be used to project the United States centenarian population. So that would mean people who are like 100 or older. Okay, so the actual number of people in the United States. We are asked to project the centenarian population in 2040. Okay, so since h of t is the population, then we should be able to evaluate the function h at some value. Now, because t is the number of years after 2015, we're going to have to plug in a value of t that is the number of years that 2040 is after 2015. So if you subtract and figure out the difference in those years there, it's going to be a 25-year difference, so 25 years later. So you have to plug 25 into the function then, okay? So just using a calculator and evaluating that out, then you should be able to come up with 259,047.13-ish. So, you can't really have a fractional number of people, so maybe this would be the population of 100-year-old people or older, right? In that year. Cool, cool, cool. And then we're also asked to project when the centenarian population will be 400,000. So we don't actually know the value of t, and that's what we want to try to figure out. So this would be equivalent to saying that 400,000 is equal to 80,040.68 times by 1.0481 to the t for some certainty. Okay, so a nice kind of easy way to be able to figure this out, for now at least, would be to kind of take a graphical perspective to this. So you could take the exponential function that we have and be able to enter its equation. Either in Desmos like I'm using, or in your own graphing calculator, or whatever other tool you might want to use. And then also create a graph of y equals 40 or 400,000? 400,000, I think it was, right? Okay. And once you do so, you should be able to, on your graphing calculator or Desmos, be able to figure out some place or some point in time at which the graphs of these functions will cross one another, which then should tell you that point in time. So when I tap on that point right there, I can find that the intersection is at 34.248. So that would be the value of t, about 34.248, right? So when t is about 34.248 years after 2015, That would be the approximate time where we expect a population of 100-year-olds or older people in the United States, right? Lovely. All right, and then kind of the last cornerstone piece to exponential functions that we need to be able to hit now is dealing with this final little section of content here. So we're going to suppose that $1 gets invested for 1 year into a compound interest account that accrues 100% interest. So what this kind of looks like then is you would take your $1 investment, and because it's accruing 100% interest, it's growing at, it's doubling basically. So what this looks like using a compound interest formula is it's going to look something like this, where you do 1 plus the interest rate as a decimal. So when you change 100% to a decimal, just equals 1. And if we were to just do this compounded annually to begin with, then this bottom over the fraction right here would be a 1. And then we're just going to do that to a power of 1. So this uses a lot of specialized knowledge about compound interest. So if you haven't ever used compound interest before, this is probably pretty foreign to you. If you've used compound interest formula before and you know it, then this should be pretty easy to understand. Don't worry about actually understanding the compound interest formula. It's not a huge thing, but it's something that I need to be able to use to show you where Euler's number is going to be able to come from. When you figure this all out, you get 1 times 2 to the first, which is going to equal 2. Basically, moral of the story is then is you'd end up with $2 after 1 year of time. Now, what we can actually do is we can actually add interest into your account more frequently than annually. So banks actually do that with your savings accounts or checking accounts. They'll add interest usually like monthly or whatever. So maybe if we were to compound semi-annually, that would mean that you would add interest into your account twice per year. That would look like this, where you would take your interest rate of 1 but divide it up into 2 increments, and then you would earn interest twice per year, so the exponent would become a 2 as well. And then if we evaluate this, this would be 1 times 1.5 squared, and this would equal then 2.25. So you would actually end up with more money after 1 year of time if you earned 50% interest twice during the year instead of earning 100% interest once during the year, right? So actually, as you keep going, and if you're to compound, let's say monthly, or maybe even if you just like went daily, so you would earn interest every day, but your interest rate of growth would be just 1 plus 1 over 365, which is a very small percentage of growth. But if you do that 360 times, it actually has a decent effect. So this ends up being about 2.7145. So you'd have like $2.71, which would be way the heck a lot more than $2.25, right? So we could maybe even earn interest more frequently than daily, maybe by the hour or the minute or the second. So is it possible that we could even earn interest continuously? Meaning that we could add money into your account literally every moment of existence. So it would kind of look like 1 plus 1 over infinity and then to the infinity, sort of. Okay, you can't really plug in infinity because it's not a number. But it's kind of the idea of it. Would that be able to equal anything? And the answer is yes, okay? And you don't actually get an infinite amount of money. It actually comes out to be about 2.718 and then has decimals that go on forever. And that's a very special number. It's a number that we call the number E, which is named after Leonard Euler, a very famous mathematician. So Euler is just the last name of its mathematician, and Euler's number is the number E, which is about 2.718 and okay? So it is an irrational number, like pi is an irrational number, right? Pi is 3.14159 and has decimals that go on forever, and there's no repeating chunk of digits. So the same thing is true for this number E as well. Your calculator should be able to have somewhere on them the E button to be able to utilize. Okay, and so it's definitely something you'll want to find. So on graphing calculators, they are above the division symbol, so you just have to push second and then divide to get E. So on whatever calculator that you normally use, find a place where you can be able to type and evaluate with E, because you'll need to be able to do that. So we're going to look at some exponential functions that involve this number e right here. So just keep in mind that this function right here, f of x equals e to the x, is basically like y equals 2.718 to the x, right? So making a little table of values for this graph right here, if we were to plug in, let's say, 0 for x, we would have 2.718 to the 0, which is going to be 1, right? If you raise it to the 1 power, it's still going to be e, which is 2.718 approximately. If you square e, so do it in your calculator, make sure that you can check that e squared comes out to be about 7. I believe it's 7.36 off the top of my head. No, it's like 39. Okay, so then if you do like -1 and e to the -1, I think that's the one that's about 0.36, yeah, or about 0.37. There we go. And you do e to the -2, it's about 0.13. Okay, good enough to get some rough points. So when x was 2, we said it was about 7.39. When x was 1, about 2.718. It's crossing through 0, 1, and then at -1, it's about 0.37, -2, 0.13. So there would be the graph of y equals e to the x, right? So if you compare it with some other exponential functions, like maybe in red if I do 2 to the x, 2 to the x should go through 1, 2, and then 2, 4, and then 3, 8, and go something like this. So you'll see that y equals 2 to the x actually grows slower because it doesn't get as high as quickly. That's because 2 is a smaller number than e, because e is 2.718, right? But like in the green, if I do y equals 3 to the x, it actually does get to 3 at 1 and then 9 at 2. So 3 to the x would be like an exponential function that grows faster because 3 is a little bit higher than e, right? So then the only other things that you really just need to work with in terms of graphing is just doing the different transformations of these functions. So we already talked about this, so I can just mostly gloss through this information here. So you're asked to graph the exponential function y equals e to the -x. So if you plug in a negative with the x, that should reflect it sideways. So you would just then need to take the graph that we just did and reflect it sideways. So at -2, then you'd have about a 7.39 y value. You have about a 2.7, a 1 y value there, 0.37, 0.13, right? So just reflect it sideways based on what we got earlier, right? You can also make a table of values based on that function too, right? And then here, this is just going to shift the graph to the right too, right? So as long as you kind of know that it's going to go through 0, 1, 1e, 2e squared, right here is about e to the -1, like that. You could sketch that out and then sketch a new graph that's just to the right too. I'll just move mine to the right too, and it'll kind of look like that, right? So nothing too crazy. Right here, I'm not really super concerned about what that -0.5 multiplying with the x is going to do. So this is not really an example that's going to be a concern for us right now. So I'm just not even going to do it because it's not a huge concern for us. Same thing here with the negative multiplying with the x. It's something that I've kind of thrown up. So the other stuff, you know, if there's a negative in front, you should be able to reflect upside down, and adding a 1 makes it go up. But you saw all that stuff happen earlier, so it's stuff that you can just be able to translate over with e to the x. Doesn't matter what base it is, right?